This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Good afternoon, everybody. Welcome to our fourth lecture in Foundations of Spatial Engineering. Today we'll be talking about networks. But before anything, there's more admin stuff I would like to share with you. Let's start with assignment 4. So if you have not emailed me or have not enrolled until last night, midnight, you've missed your chance. You're actually not going to be able to do the assignment 4 at all. So if you're not in, you're out basically with assignment 4. Then assignment 3 will be released next week. It's your major assignment, your GIS project, and you'll be divided into groups. The groups are formed by us. You don't actually get a choice to pick the group. That's mainly for organizational reasons to save time. So we've already created a group and we'll release them sometime later this week. And the groups will be formed within the same lab you sign in to attend. So if you have requests that you would like to be in a group with a friend, it is possible, but you have to be in the same lab. Otherwise, no chance. Then next week, is it next week? Yes, already next week. We'll have the guest lecture from two gentlemen, David Jones and Michael Rigby. So Mr. David Jones is a curator of Map University Library map collection. And so he'll talk about many of the valuable map resources and data resources you can use for your assignment 3. So make sure you come and pay attention because he will really share good source of data and other information that are for free. I mean, like Mr. David Jones can both show the data sets that you can access for free and some which you can access through university license and their system. Similarly, Michael Rigby, he will talk about ORIN, which stands for Australian Urban Research Infrastructure Network. There's more data available in ORIN or through ORIN, but they're licensed and they're available to you through university services, so you can use these as well. Oh, too fast. So it's good to come next week. Then 2 weeks after that, in week 7, we'll have mid-semester test. We'll write it here in this theater. We all can fit, so it should be fine. And there's plenty of examples on LMS. If you cannot access them, it's right at the bottom, the front page, I think. And we're also thinking about creating some quizzes for you to review the material from each lecture for the week until the next lecture. We might start next week, we'll see how we go, but generally it will be then when this lecture finishes, there will be a quiz available for you on LMS which you can take. It will immediately tell you which answers you've done right or wrong and give you some feedback about what you remember. These quizzes, these tests won't be assessed. but there for you that similar questions can then appear both on mid-semester test, but definitely on exam. So if we won't make it before mid-semester test, then definitely use the quizzes as a practice for exam. It will be small questions. If it's multiple answers, maybe like 3 questions. If it would be some computational question, maybe just 1. So you do the calculation and you submit you pick the correct result, and so on. So if you have any ideas, any suggestions for the quizzes, feel free to tell me or email me. We can have your feedback even before the quizzes start. So if you had some experience with quizzes in other subjects, other lectures, let us know. Just again, I want to reiterate, these quizzes will be available only for that 1 week. You can have multiple attempts to do them. That's the plan. You will have multiple attempts and then they will disappear. So it's for you to practice. But of course, you can write them down once you're doing them. Do you have any questions on me regarding the admin stuff? Any assignment? Yes, Mohammed.
Regarding the group formation, all our group members are within the
Same lab, yes.
Same lab. Then do we just send an email that we want to be in the same group to our workshop?
You can do it in the lab, while you're in the lab, and say the 2 of us wants to be together, and they can do some adjustments. But
the group size actually.
pardon? No, 4. We had to increase the numbers because there's a lot of you. Yes, around 4, sometimes maybe 3 or 5. Any other questions? Any? Pardon?
I would bring the calculator with me someplace.
Bring the calculator. It's a good question. I don't remember how we did in the past, but I'll have a think. It's a good question. Calculator. Maybe just like the hand one, like the basic one. Pardon? Well, I don't know if you're calculating the I don't know, some matrices or things. You might want to remember some numbers. I don't know. It's a good question. I'll come back to you. Any other questions? Good. I know quite a few of you had questions on me in the past 2 weeks, and one was about interpolation. So I'll show you another example of raster interpolation, so hopefully it will make more sense to you. So on this slide, as it says, that raster interpolation can help us to predict or calculate the values for cells where we did not have any information. So if you imagine that this is our measurement field, and on these points we've measured the values that are presented there. If we overlay it with grid cells, so we can immediately say, so these grid cells will have value 30, 27, here's 20, 16, 24, 20, and so on. But what about these ones? How do we decide which values to assign to these other cells? To decide which value to give them, that's why we do the interpolation. So we can either then do the nearest neighbor. So let's make it easy, for this one, nearest neighbor would be 30, this one, nearest neighbor, 27, and so on. So with this one, how do we decide? Well, we can toss a coin or we can use a different interpolation. That's why the main purpose behind interpolation is to get values in locations in cells where we don't necessarily know them. Yeah? So this is an example from Esri. So we can see that in these cells we have the values that we could measure, and in the rest of them they're calculated using a specific algorithm. My guess is this would be something like Kriging, which is not the one I've shown you, neither one of those 3 I've shown you 2 weeks ago. So you don't need to worry about how that's done, because Kriging would be using the whole data set. It would be a global algorithm to determine on interpolation. But I hope just looking at these 2 images and see how you can approximate the values for these, how that can help you understand why do we do interpolation. Just to reiterate again that interpolation predicts the values for cells in a raster form in a limited number of sample data points. So it can be used to predict unknown values for any geographic data like elevation, rainfall, temperature, noise level, different concentrations, and so on. These are just examples. Another example, a little bit zoomed out, so this would be measured elevation field points. So when we know the elevation at each one of these points, but we want to show the whole terrain using raster, so we would run the interpolation algorithm, and it will immediately give to every pixel, every raster cell, the elevation terrain value. Does it make sense? Does it clear the interpolation for you a little bit more? And then the three algorithms I've shown you, those that you can actually process and calculate yourself. That's the nearest neighbor, bipolar, and is it binomic? Bicubic, bilinear and bicubic. Damn, lucky. Also, because last week I was rushing towards the end, I've realized, based on the questions you've asked me after, that the point in a polygon is still not that clear. I believe this option is very clear. If the north is confusing you, you can forget that. That's actually, I mean, the line that points north. Imagine that it's just like an x and y axis. You should put the polygon into some reference system so you actually know where you're measuring it, so the angles make sense. That's why the north line is there. If it's confusing you, don't worry about it. But in this case, everybody, I believe, can see that it's 360 degrees if you sum all of the angles. I have another image for that, a little bit more simplified. It's important to go within the same order of the angles. I think in this case it's easy, so we have from angle between 1 and 2, this 1, 2 and 3, and 3 and 1. I guess it's easy to see that it's 360 degrees when the point is exactly inside the polygon. However, when it's outside, why is it 0? How come it's 0? So you create the lines that connect the point with all of the points at of the polygon. And what's important, you again mustn't forget about the order of the points. This is a little bit more complex, so let's look at it in a simpler version. So if I look at between 1 and 2, that's this angle over there. Between 2 and 3, another angle over there. But between 3 and 1, I'm going the opposite direction. So if these two angles are plus, the third angle will actually erase basically what I've just measured. So it will be the same amount of plus angle numbers as the minus. Does it make sense? Good. Good. It's good that you give us feedback so we know that certain things can be explained better as well.
Because I guess we always select the short angle.
Well, the order is important. So I'm going this way from 1 point 2 to 3. If I would just go randomly from 1 to 3 and measure it somehow, it would not give me 0. But it's always important to keep the order.
From 3 to 1, you can go for the longer path as well.
Oh, you mean you would go the outside way? But it's not really the angle within the point and the shape. That's the outside angle. Don't question it too much, just look at this graphic and follow the order, okay? It will work. And if you can measure the smaller angle, you do measure the one that actually points between 1 and 3. That is, let's say, in direction to the shape. That's why you don't want to go outside. You want to have it in direction to the shape. Yep? Okay, networks. So we've already talked about rasters 2 weeks ago. That's one way of representation data in geographic systems. Last week we talked about vectors, and this week we will talk about networks. You can think of networks about another way of representing spatial information. It's very similar to networks, to vectors, because it's using points and lines, but they're called differently in networks. There's two different ways of naming networks and points and lines, and I'll be using both. And I'll follow the terminology that Dr. Stefan, the Professor Stefan Winter uses for this subject as well, because I think that nicely distinguished it. So in networks, we're using points that would be called nodes or vertices, and then we're using lines that are the connections that show the relationship between nodes, and they can be called edges or arcs. However, these connections, these lines that connect two points, are only logical. There's a logical representation of some connection. It doesn't necessarily mean there is a physical link between those 2 points. So they are not describing the geometry, the lines in networks. Not necessarily they can, but don't have to. They show a relationship. And as opposed to vectors, they are not meant to be a straight line. They can be curves or other shapes, just any other way you can think of when you want to connect 2 points. Okay, so hopefully some of you have done some reading. So let's look at our first poll. And it's still not working for me within a presentation, but you probably already got used to it. So what are the most common network operations? And this is again not working. Interesting. Duplicate. Navigation, that's a good one to start, really. Any other ideas what we can do with networks, network operations? GPS, yes, that's very connected to navigation. However, GPS would be that's the system, that's the reference, global positioning system. Shortest distance, that's really good. Tracking as well, you're tracking paths, yes. Emergency, that's a really good example, good use of networks in emergency cases. You'll hear an example from me later. What else we have there? Tracking, analysis, shortest distance, alternate routes, optimal paths. Yes, all looking at the paths, really good. Shortest path, shortest distance. There are differences between distances and paths, so we will talk about it as well. Traffic, also a very good application of networks, one of the most common one. Seems like you were all very familiar with networks. That's a good start. Any more responses? Okay. Thank you. If you want, you can carry on sending messages, but I'll continue with the presentation. So these three terms here, pathfinding, tracing, and allocation, would be the three most common terms describing some analysis that you can apply on networks. So keep that in mind. I'll be talking about variations, about all different network operations, and these three will come into play, definitely. So we'll talk about pathfinding, which is some of you mentioned trying to find the shortest path or the least cost path in a network. To decide on that, before we decide on that, we're asking question, how far is something? How do I find a way to somewhere? Next is tracing, to determine a connected portion of a network by a flow. Can I reach something? Generally imagine with some water graphs, water flow. Can I reach certain sea by following this river? That would be tracing. That you would trace the flow of the river, the direction of the river, and see where it is, if it can go where you're heading. Or allocation, to assign portions of a network to a specific location. So with an emergency example, that's an allocation task, allocation problem. So what is the catchment area for example, certain hospitals, where you have accidents that happen somewhere? So which emergency team you want to send there, which emergency is the closest, so you will do allocation algorithm. Or yes, an example, which ambulance should then reach that. So keep these three options in mind: pathfinding, tracing, allocation. We'll be talking about them in more depth later today. Some network examples to show you there's more diversity in networks, that it's not all just transportation networks. However, they are the most common one. So an example from a transportation network in Auckland, showing the traffic links and the traffic congestion, or links where it's good and you can nicely drive through. Other transportation networks can be also showing the tram and train line, or bus connections. Any urban street pedestrian network is also a transportation network, or you can show freight distribution. Airline network is also a transportation network, but it has slightly different parameters, because you can see that there is not a physical connection between Melbourne and Sydney in the air. It's not that train has tracks, so there are no tracks in the air, and the connection maybe happens only few times a day. So it's not every time. The connection does not exist all the time. It has some schedule, and the connection happens only depending on the timetable. But we can still call it a network, even though it doesn't have a physical. Doesn't have a physical environment. That's what I mean. Also, ski slopes can be seen as a network. They have roads as well, but in ski slopes, I guess it's more obvious that they have direction. You generally want to go downhill. On a ski slope, you can go uphill taking the lift. So this would be up. And these are oriented network links that they show the direction down, and all self-connected. Yeah, but generally speaking, transportation networks are the major topic where the networks come into play the most. They're mostly used in transport. Another example is the tree-like network. This is an example from hydrology, showing the river streams. And why is it called tree-like network? Imagine that this is a tree and it branches out to all the different streams, and at the very end we call that a leaf. And the properties of a tree network is that from one leaf I can take only one path back to the source. It's called source. In the river it doesn't seem like it might be the other way around in the logic with the rivers, that this is where the river ends, where it reaches the sea. But in tree terminology, in tree graph terminology, it would be called the source and the leaf at the very end. Specific parameters about that is that they are acyclic. Means you cannot create a circle. The water can't flow in a circle on land. Unless we help it somehow mechanically, it wouldn't be able to flow in a circle. And there's only one path. It's the shortest path trees. Usually water is a good example. It will find the shortest path how to go down. It wouldn't wind around locations where it would be slower. And some examples that some telecom and LAN networks can also use the same model. Yes?
Can it split at the region?
No. No, because you will be creating a cycle there if you're splitting and connecting. I have here another example of the tree-like network. This is reaching from my office to different locations. I mean, like, you can share a certain bit of the network. So this bit is shared between those two locations. But you couldn't actually split that because no, that wouldn't be a tree. That wouldn't be a tree structure. Could still be a network, but a different structure. So it's acyclic. So if this is where my office is, so these are the shortest paths to this building, for example, Union House and library. So there's only one way, which is the shortest one, only one way, one option that will give me the shortest path. And the ends, so these would be the leaves, the dots.
Does it have to be always the shortest? Not necessarily.
It has to be the shortest, yes.
But for example, for catchment areas, not every time, not all.
That's a different network, yeah. That wouldn't be a tree-like.
Hydrography,
That wouldn't be a tree-like network. For
there's many examples like catchment areas, like in the previous slide.
oh, you mean catchment of water, not catchment for the ambulances and that. But that still will be the shortest path. Yes, the water will still find the shortest path down. You would argue that, you think? Well, because there's some barrier. So the barriers can create it, kind of like make it longer. But if you have an option to go through the barrier, you would go through. So it can look like it's not the shortest path because there would be some barriers which we don't see. But generally, yes, the shortest path, including the barriers.
And what means shortest path trees? Is a kind of?
Pun?
Or shortest path trees include all of the examples on top of the
Yes. Well, yeah. This example is of the shortest path tree. I can have a tree. So I could reach that destination to go all the way around. And think, is that what you mean? That I could reach the destination to go all the way around, but that wouldn't be the shortest path, pardon?
So what I mean is a tree-like network, which look like that.
Yeah.
But you are not following the shortest path.
Yes, okay, I've got you now, yes. Thank you for your patience with explaining that what you mean. Yes, I can reach that destination using another path, but that wouldn't be the shortest path tree. Generally, we don't create them as much because they're not that valuable to us in network settings. But it is still possible. It still would be a tree-like network setup. Yeah, but think more of the shortest path trees.
Would the example that our colleague gave be in a context of maybe lowest cost path? So for example, maybe the shortest path in terms of like steps or roads you need to take might not be the best path to take because you have a higher cost like traffic congestion, for example.
Yeah, exactly.
So
Exactly.
in that situation you have alternate routes based on different heuristics.
Yes. Different cost values. However, in say a road network, that wouldn't probably a tree-like network, but yeah. Good thinking. Yeah, I just wanted to say that single leaf, the leaf structure is where one single leaf is at one end of the tree. That's the shortest path. If it wouldn't be the shortest path, I can have more leaves at some ends, but with the shortest, it's just one leaf. So this is the short, there's only one option to what is the shortest. Yeah, there's only one leaf that goes exactly way back to my office. There's no other choices, there's no other cycle. There's only one shortest path, just from logic perspective. Then we have other networks, for example, computer networks. Some can have tree-like structure, but for some local computer network setting. But if we look at internet at large, around the global internet, then it's much more complex network and it can have cycles. If you think about it, when you send an email to somebody who lives on the other side of the planet, it doesn't care which way around the planet the email goes. So there can be different cycles. So these networks, they have multiple choices. They're much more complex. They also have some, they are based on some physical infrastructure, means we have wires and systems. And they're very much open to wide network analysis. There's a whole different field of network analysis based on computer networks. Other networks we can mention are social networks, where the nodes are not based on any location, but they're based on people or animals, or say, for example, there is a supply chain or where my money flows. So if this would be the network of the friends I'm connected with somehow, for example, on Facebook or other social media, or it can be my income streams. So these can be the resources where I receive my income, other streams, again, within a connected network, where do I spend my money? So this would be some kind of network as well, but we would call it a social network because we don't take the location, the coordinates, into account. So the nodes are not based on location, but based on people or other moving things. So if it's based on my social network, the people can still move. They can be at a specific location at some given time, but we don't account that within our network. It's the connection that matters, the relationship. But within this subject, we will look at spatial networks that are embedded in space. So generally, we will have coordinates x and y, sometimes z, for our spatial networks. And we were looking at the position in spatial reference system. As opposed to non-spatial networks, like the social networks where the position is as convenient. I'll show you an image. It doesn't specifically say that this is a set position for these specific connections. It can be spread even across the page, across the world, in any way. By using coordinates for spatial networks, that allows us that we can argue and calculate things, for example, the distance, the cost of different distances, the cost of different edges, like what you've mentioned, that it can be the cheapest path or the shortest path. We can think about the fare, we can think about the speed, and that all, to do this calculation, it allows us because we know the locations of these points. When we have no coordinates, sometimes it's hard to then decide, not sometimes, it is then hard to decide what is actually the value, what's the cost between the connection. But with coordinates, it's set within the coordinate geometry, so that helps us. I might have answered my question, but there's another question. Are social networks spatial? What do you think? Nobody? You can just shout it at me, that's fine. Yes, okay. Really? There can be spatial. Context dependent. That's very good. I like that answer. Thank you. I was just thinking it is maybe not the best word clouds to create with. But yes. Spatial networks depends on the context. So we can measure the location of our spatial nodes at any given time. But we're not interested in it. I don't care where my friend physically is, as long as I'm connected to them somehow.
Social networks, doesn't that also take some sort of spatial references into account? Like, for example, not only is this a friend of a friend, but this person is also in proximity close to me. Thus, I would suggest said person to you as a connection.
Yes, that's true. But as you know, that person had to tag their location somewhere or mention their location somewhere, saying that they're also in Melbourne. So they themselves specified their physical location, and based on that you can then place it into the algorithm for friend suggestion. Yes, that's possible, but it's not the primarily meaning or primarily connection between you and this friend. So you're not primarily friend with your neighbor just because you're both in the same classroom. Does it make sense? But if you both tag yourself that we're both in this classroom, then the algorithm can pick up, oh, they're both in the same place, maybe they should meet and become friends.
So only if that spatial context gets added into the suggestion.
That would be added, yeah, that would be added into the suggestion, yes. So that's then you can measure the location of all of these nodes in social networks, but you're not primarily interested in it. So some network concepts. This is where the terminology will come into play. So we have graphs. I'm sure you've all heard about a graph theory. So graph is by definition a set of vertices and edges. So this is where we'll use a certain terminology. When talking about graphs, we will talk about vertices for the points and edges for the lines. Yeah, vertex, the point, edge, the line. There's also some way how it's written. So we're using capital letters. The big G, V, E, G, graph, V, vertices, E, edge. It means for a whole set. If we use the capital letters, we mean the whole set of the graph. If I would use non-capitalized letters, I would think only of the individual one specific vertex, just like one Melbourne, one point, or one specific connection. There is one condition when we talk about graphs, and that is that a set of edges is a subset of two vertices. What does it mean? That the set of edges, see this connection, edge is the line, edge is the connection relationship in graph. So this connection between Perth and Melbourne, that's an edge. And it means that it's a subset of two vertices. So it's a vertex for Perth and vertex for Melbourne. So you cannot have an edge without the vertex, basically. So if there is no node, if there is no point, you cannot have the connection. Means that the edges are dependent on the vertices. And they're not necessarily a straight line because they're only showing the relationship. This is a good example because the lines are not drawn straight. So it's showing that there is a connection. As opposed to vectors where when you connect 2 points, it's always straight line. So not in networks. We have two different types of graphs. We're looking at directed and undirected graphs. So in undirected graph, we have unordered pair of vertices V. So if we look at point A, I can see that A is connected to C, B, and D in any direction. So it's an unordered pair of vertices. It doesn't say which one comes first, which one is the start, which one is the end. However, in directed graph, we order these vertices. So if I look at point A in directed graph, then I'm only going out from point A to C. That's my only connection from point A. But to reach point A, I can go there from B and D. So it's a directed graph. So we're distinguishing in directed graph between the start vertex and the end vertex, the start node and the end node. There's a specific notation that the first set of brackets, the curly brackets, are used for unordered, for undirected values, generally mathematics, same with graphs. And directed, we would use the round brackets. So if we know it's directed and ordered, we can write it like that. So it's a principle from mathematics for ordered sets. A special case of graphs is something we call the complete graph. It means that the graph is complete, that every possible relationship between any pair of vertices is drawn, is happening, it's connected. So complete graph represents every possible relationship between any pair of vertices. And it's written with a capital K. So we see this is a complete graph of one vertex, complete graph of two vertices, three vertices, and so on. So all the connections I can draw between those 4 points or 5 points, if they are present, that's what we call a complete graph. Another example of terminology when we talk about graph is something which is called bipartite graphs. And it means that we can we can sort our vertices, our points into two classes. And then the connection happens only within these two classes. What do I mean by that? It's really good to see on this example. So we've divided our network into M and N set of vertices. So M represents the cities and N represents the states. And we can only connect where the cities are within a specific state. So we see Sydney, Newcastle are in New South Wales. But we cannot make a connection that Sydney is within Brisbane. So that wouldn't make sense logically. The same with the states. We cannot have a state within another state. So these are the bipartite graphs. So we sort the vertices into two classes. So we have the set of M and N, and only one relationship between M and N can be, not one, the relationship can be formed only between M and N, not within. And there's an example again of a complete graph within the bipartite if all of the possible connections are reached. So this wouldn't be a complete graph because we couldn't connect Brisbane to New South Wales. Yeah? Planar graph. Planar graph is something where we can connect the edges in such a way when we can connect the vertices in such a way that no two edges intersect. So we have the nodes, we have the points, and the way how we connect them, they don't intersect. So that's something we call planar graph. We can be drawn on a plane with no intersection. So keep that in mind, no intersection. So there's a question for you again. So which statement is true? A complete graph of 4 nodes is a planar graph, or a complete graph of 5 nodes is a planar graph, based on this definition, that no edges, no lines intersect. Can you do it with complete graph of 4 or 5 vertices? What do you think? Pardon? It's not the option there is, but should have included it. That's true, actually. That would confuse you even more. Are you all voting? What do you all think? 100%. That's pretty good. I wonder how many people actually responded. It's just 1% thing. Any more votes? And you want to know the solution? I'll show you in a minute. By intersect that they do not cross. So which one of these planar graphs are, which one of these complete graphs are planar? What do you think? Pardon? The first 3, that's easy to see, definitely. Those are planar. None of these lines intersect. What do you think about the K4? Pardon? It is a spatial graph, but can you make a connection? You actually can. It may not sound intuitive, but you can create a connection like this. That's the trick with graph theory, that the lines are not straight lines. They can be arcs and they can go around. So if I can make a connection between this point and this point to go around, it's still planar graph. But no, the complete graph of 5 vertices is not a planar graph. If you ever find a solution to that, to connect these points, then great, let me know. You might win some Nobel Prize. Trees as graphs. What's going on again? For some reason, it doesn't want to always duplicate my screen. And now you see it exactly how I see it, which is not. So we have trees as graphs. The definition, the tree is a connected acyclic graph. Means you cannot go around this graph. There's no node or vertex that is connected, that is not connected with the rest of the graph. So there wouldn't be like a standalone part of this graph. They all have to be somehow connected together. So there's no cycle. All nodes are somehow connected with the rest of the graph. And we cannot travel in the cycle as mentioned. And they vary in complexity. A good example is the water flow catchment. It's a typical example. But the more complex trees we get, the more complex computations can be done on them. Now we've come to networks, from graphs to networks. So we can distinguish between graph and networks by giving a certain edge some cost. So if I'm only talking about the pure connection, if there is or not there is or isn't a connection, I'm talking about a graph. But if I already give it some cost, give it some network value, then I'm talking about the network. So network is a weighted graph, where a cost is attached to every edge, or even some of the nodes, some of the vertices. So to distinguish from the graph, so graph is using edge and vertex, and network is using nodes and arcs. So this is an example of some weights. It can be, for example, the cost of the fuel that is needed to get from A to B, B to C, and so on. We can also, as I said, you can attach cost to the node. For example, in public transport, this can be a connection node, and I'm waiting there 10 minutes, so it's adding to my travel time, although it doesn't cost me anything money-wise, but we can call that at the time also as a cost. So even the nodes can have some cost. So the cost that you can typically give to arcs is for example, looking at the capacity, the length itself is a cost, travel time, different fields, fuel, and so on. And with nodes, example, waiting time, or it's a gate or a highway, at a specific point it suddenly costs you way more. Or turn costs, just because you're at one location, to turn around can again cost you some time. So what do you think? Are the major roads between cities forming a graph and so on? Let's look at that here. So are the major roads between cities forming a graph, network, undirected graph, planar graph, or complete graph? Well, you're almost correct. What about this one? What do you think? What would it mean, the complete? Starting at the bottom, if it's a complete graph, means that everything is connected. Is it always possible between cities?
But if it is a network, cannot be a complete graph. It's not a graph.
No.
I mean,
So some cities may not have a direct connection. So some cities you can only go through one city already. There may not be. Think about, is there a direct connection between? Now I'm thinking Melbourne and Pardon?
Even flight paths, for example, where you have stopovers,
Yeah. Yes. Yeah. I'm struggling with a good driving or a road network example, but imagine that some locations you can only access through a certain place, that you cannot cross. For example, there would be a border, or you cannot go directly from one place, from A to C, you have to go through B. So it's not necessarily a complete graph when it comes to networks.
but if you
They do form a graph if we in a certain way of terminology, yes, they do form a graph, that's correct. They form a network that's clearly your favorite and correct. And they're undirected, means that you can travel in both directions, that's correct. And none of you selected it's planar, that's good, because they can cross each other. We can have roads on top of each other, but you cannot change from one to another. And examples why they are not planar.
Which are the costs that you give to that route?
Pardon?
Which can be the cost or the weights that you allocate to those roads, to the nodes and to the...
Well, it can be the distance. The distance itself is a cost.
The name of the city is a cost now.
Unless the... Well, it depends what you're looking at. So if I'm taking in my total travel cost from one place to another, for example, in some towns can have... I'm just paying for parking can be a cost. Just to drive and be in Melbourne, I will have to pay for parking. So Melbourne, you can put the cost of parking to the node of Melbourne. Or to cross certain bridges, you have to pay. To go across the border, you have, or the toll gates. That's where you have to pay.
The graph is the basis.
The graph is the basis. It's just showing the connection. Graph shows the points and lines, the possible existing connection. But if you give it the cost, if you tell it costs me $20 to go from A to B, that's what we would then call network. And the cost can be anything. It can be time, money, I don't know, number of the distance itself. Yeah, and I think that's a good place to take a break today, and then we talk about network operations after the break and after our presenters. So we have 13 presenters for assignment 4 today. I'll bring you up. That's how I've ordered the... So for week 4. So this is the list of the presenters. In this order exactly what you can see. Can you read it well? So if these 13 presenters can just align themselves after the break, that will be awesome. Otherwise, we can have a 5-minute break, and then we'll continue.
I'm the presenter today, and I'm just joined the class week 2. Because before I didn't see the detail, it says but I usually the report at this point of the time.
the slides, and as I've mentioned, this would be the order of the presenters. Okay, about 3 more minutes, pardon?
Should we just start like this?
Yeah, you can start lining. Yeah. Yep. No, the mid-semester doesn't take max 1 hour, maybe even less. Do we have the presenters ready? So I'll make it full screen. I'll show you the order again, so you know when's your turn. You can just, the person who presents will then click the arrow and then you see, oh, that's mine, so you can just run in. Okay? So I see you know you're the first one. Put it up.
Yep. Hi everyone. So this article was taken from a article from abc.net, and it's about a Middle Eastern business trying to tow an iceberg to Dubai for water supply. And this map was on in the article. This map, there are a few good things about the map. They showed bearings in terms of where the equator is at, and where the Southern Ocean and all the different named locations are there as well. But this assumes the knowledge of the person knowing that where the equator is and where the north and south would be. Some of the bad things about this map is that there are no title, no legends, no scale, and no compass. So you don't actually know the distance between each location. So, and you can't tell which side is actually north. And yeah, and there are also no indicated country regions, and the main thing is that Heard Island is actually part of Australia. So it's not stated there that Heard Island is part of Australia, so it doesn't give the context. But it does achieve the objective of showing the relative locations. That's all.
Yeah, good afternoon. Originally, this newspaper wants to use this map on the left to describe the climate change in Michigan, but it lacks many elements and cannot explain the problem at all. It has no title, no scale, no spatial reference frame, no north arrow, and no source. Also, there is no name of any region on this map, so it's easy to misunderstand that all the land on this map is Michigan. But when we compare it to the official map on the right, we find that only the land on the left half of the map is Michigan. So the right half is completely irrelevant. And also, we don't know the name of water. And the land of Canada is also missing. So hard to say it's a good map. Yeah.
Hello everyone. My chosen article is from the Sun News on the 12th of August. The article talks about rescue drill in response to a possible tsunami. The article includes two geographical information. The first one is on the left. I think this information is well designed because it first used a high-level map to show the approximate location to the readers. Then it used the satellite image to show more details and tell the exact drill location to the readers. Because the earthquake is the main cause of the tsunami, so the author uses the second map to show some dangerous area in Europe. I think from the second information, we can clearly know how likely the earthquake are going to happen across different zones. So I think both of them are pretty clear. So, thank you.
Thank you.
Hi everyone. So this is a map from WTO website, and it illustrates the numbers of the trade agreements in the world in 2019. So this map, the color ramp is really in a harmony and shows no bias. And also the legend on the left side, it gives 5 levels of the densities of the agreements, so it can be very clear. However, the marks can be made on this map to show some regions and countries that mentioned in this article, such as the European Union. And I think it is common sense to everyone, but it will be very helpful for the readers. And another point should be improved is that the classification range should be more specific. As we can see, the second class, this ranges from 11 to 31, and when we're comparing the business relationship among different countries and regions, it is based on the agreement numbers. So I think it is very necessary to be more detailed range. That's all. Thank you.
So hi. So this is a map. It's an article about the core battle on the ban on the plastic bag or the ban prevention. So this is a map about the United States, and the special things is it doesn't use the real scale. I mean, you have 2 states, which is Alaska and Hawaii, to put from here, but it ensured all the states can be very clear to view, and so it's good to see that we can see each state has the state borders and also have the name on the state that have the law about the plastic ban or the plastic ban prevention. So this graph, I think, is very good to say out the points related to the article. And also the article mentioned 2 cities, the Austin and the Laredo, we point in the graph, which is these good things. Yeah, and also have the detail on the states, and yeah, that's it. Overall, I think in this article is a good map.
Good afternoon, everyone. This is a map from a UK newspaper called Telegraph. You can see the left upper part is a map. There are few parts of the map, and it's good for author's argument, and it has clear boundary shape, and it's eye-friendly. But there are 3 layers of drawbacks of the map. The first layer is some lack of some basic indicators. It will do harm to your reader's experience if you are not familiar with geography and some name of country in the West European. And there are also some advanced issues. First, the title is not appropriate.
Actually, it's a map of the carbon intensity in West Europe, but not the energy consumption all over the world. Maybe you can see a small size, but you cannot see everything. Yes, the most important issue is lack of legend and metadata. The reason why this situation happened is that it's a snapshot of the GIS system. So when we refer to GIS system, which is of rich information and user interactive, you cannot only do a snapshot of some part of this system. So this is what we should learn from this picture. Thank you.
Hi everyone, this is a map from the recent news article talking about an explosion happening in northwest Russia. The article intends to use this map to point out the explosion sites as these red circles indicated, but it has some problems in this map. First, it's no referencing. So it seems like this map is just cropped from a big world map, but there is no reference to that original map. And second, there's no legend, so without the news context, we have no idea what the red circles are represented for. So the second thing is, it is quite strange that they have labeled all the country names surrounding by Russia, but they didn't label the country name Russia on the territory. So it may cause confusions. And finally, it's unclear that where the article get the source of explosion site. They have no coordinates, so it's not a good map. Thank you.
Is that you?
Hello everyone. News I'm going to talk about is an earthquake happened last week in New Zealand, in the South Island. This is a map they use in the news. There are some issues with the map, I think. The first one is because the location is map on sound, but it's not showing very clearly in the map because it shows on other squares which represents other earthquakes happening in a year. And the second issue is it does not include any legend which show you the meaning of the color. We can assume that a darker color will mean a stronger earthquake, but it'd be nice to have a legend to have some reference. Yeah, thank you. Thank you.
Hello everyone. This is the geographic information I'm going to present today. So let's talk about the advantages of this map. First, because of the informative title, we can easily understand this map is about two different zones of gamba grass. The wide distribution of gamba grass has led to some serious problems, like wildfire. The author used two different colors representing eradication zone and control room. Also, the overview sidebar side map gives us more locational context of how gamba grass spreads. But there are two different ways to improve this map. First of all, it should provide the date information for this map so that audience can understand if it's updated. And also, it should provide the legend for white lines between cities. Yeah, that's it.
Thank you.
Hi everyone. I found this map in recent news, which mainly talks about the environmental disaster news as February flood spread the prickly acacia in a lot of areas. And this map is about the distribution of prickly acacia in North Queensland, which is pretty relevant to the context. And that's one of the good things about the use of this map there. And there are also other advantages like harmonious color choice, and there's mini map provides in the bottom right column, and which provides the audience the location reference, and it contains the basic map elements like titles and scales and so on. However, there's still some drawbacks about this map, like lack of data or overload of information. But overall, it is an instance of making good use of geographic information in the media. Thank you.
Hello everyone. This is an article from the Time magazine showing that Trump wants to buy Greenland. That article references a map from 1947 made by the same magazine. From the map perspective, it shows the wrong Arctic circles, which is not like that, and it's not centered by the Greenwich meridian, which is a convention. And the third, it has no scale. From the use of the map perspective, it did show the reason behind the idea of purchasing Greenland, which is the military importance of that place. However, it used the red line to circle the USA territory, which is not neutral, which makes people think USA is aggressive in military, which is actually is. Thank you.
This is a map from the online news report. Murder happened in the United States, and the good thing is that it has the title tell you the red point is where the murder happens, and the source is the Google Map. But it's just a screenshot of the Google Map, so there is no legend tell you what the color in the map means. But we can assume that the green one is a path, something like that. And there is no arrow and no scale bar. This map is zoomed out too much, so it miss some details about the road, the building. So we can hardly tell that the location, like the direction of other buildings, something like that. And it has no crater tell you what is source created by what is not created by someone, something like that. Okay.
Alright, this is a map of the Christmas treatment of Adelaide, and you can see as the picture, it has a north arrow, it has a scale bar. It does not contain a title, but on the corner it tells us it's a Christmas pavement. But it's lack of the legend. It doesn't have any special frame, and it does not contain any production information. So as a map, it tells us the date of the pavement. But it does not tell us the exact time, and the map does not tell us about where it is. You can only know from the endpoint is the city of Adelaide Town Hall, but where is Adelaide? It's the West Australia, and we don't know. And from the article, it tells us the Adelaide Christmas pavement has changed the route, but we can only know if the end point is the town hall, but we don't know the original route, so we don't know if the road is changed or not. So that's all. Thank you.
Thank you. It's also an example of a network, if you think about that. You see? Probably not the shortest path, but maybe the prettiest part with some nice cost examples. But if you go this way, you will see the
the most beautiful things. Maybe. I don't know. Thank you. Thanks to all presenters today. And we can look at network operations
for the rest of the time. First thing we can measure with networks is something we call a degree of a vertex. A degree of a vertex is the number of how many adjacent edges, means how many lines, can go away from a specific vertex. So in the undirected graph, which would be the top one, I just sum the number of lines they go into it, the number of edges. However, in the directed one, it's getting a little bit more complicated. I need to distinguish between in degree and out degree. So for the red line, how many in degree lines does it have? 2, yes. And out degree? 1. Great. Seems like you understand it very well. So the first one has 3, degree of 3, and the other one has just 2 and 1. Once we know this information, we can also do some statistics with them. We can do histograms, standard deviation, and so on. Generally, in a road network, most of the degrees, we would have about 4, that one intersection can have 4 different roads leading into it. So if we do a histogram, it would peak around 4. So that's what I mean when I say you can do statistical analysis with the degrees. But just to give you the solution, so yes, that's correct. So 3, in degree 2, out degree 1. Then we have something what we can characterize in a network, which is called walk, and it's a connected sequence of degrees. Like in the last presenter's examples, thank you, it can be called a walk. So it's a connected sequence of degrees. Of edges, no degrees, sorry, I'm not even reading correctly. A connected sequence of edges. What does it mean? That I have a start node that leads to its then the edge leads to its destination, and the same node becomes the start node of the next edge, the next line. So each interim destination has to be identical to the next one. Can we have self-intersections in walks? What do you think? Can they intersect the lines in a walk? Generally, when you walk through a park, can you intersect your own path? Yes, you can. It's possible. So some examples of walks. This one, we can go zigzag. I start here. There, I can cross my own path. In walk, I can also use the same edge twice or more times. I can visit the same edge multiple times. I can visit the same node multiple times. And it will still be called walk. Walk in a graph. Then we have paths. Path is a walk with no self-intersection. So we expect the same connectivity, but each one of these intermediate nodes won't be a path. So because I'm already crossing my own path here, this is not a path. This will be only the walk, but this can still be a path.
What do you mean by self-intersection? Why not just intersection?
Pardon?
It's self-intersection. Why not just intersection? Why the significant? What's the significance that was?
Thinking about it, you're trying to find the optimal path, go from point A to B. If you're intersecting the way you already went through, you're actually not fulfilling the task. You're not finding the optimal path. You're just walking around without any specific destination needs. So imagine you're walking in a park. You can really go zigzag however you want. You're walking and talking. That's okay. You can go whichever way you want. But if I want to find the shortest path from my location to the station, I don't need to do zigzags through the neighborhoods. That would really not help me to get to my destination. If I do the zigzagging, I'm just walking. I'm killing the time. Think about it with this logic. That path is that you really want to find the optimal route somewhere. So that would be called path within a network. Does that make sense? If you're happy to wander around, that's a walk. But if I'm crossing the streets and it's like, oh, I've already visited this corner, let's go this way now. That's a walk. But with a path, you see, oh, and then I turn right at this corner because then I turn left, and then that's where I am. Yeah? Keep that in mind. In paths, no intersection. And I cannot also visit the same node. So the first one, I'm not sure which option. None of those will actually show it, but in path, I cannot visit the same node. It wouldn't, again. I'm trying to get from point A to B, so I don't need to be in point C twice, because I want to go through and go to my destination. Then we can talk about cycles. Cycle is a path with a specific condition that the start vertex is the same as the destination vertex. So we talk about connectivity. There's again no possibility of intersection between, except for the first and last one. So I can visit the first and last node twice because I start there and I end there. So that's the only case where I can have intersection in a cycle. So none of these are a cycle. I think it makes sense. But these could be cycles. Triangle is a cycle. K6 is a cycle. This can be also a cycle, even though it looks like it intersects. Why do you think that can be a cycle? Yes, because I can go. It's showing the connection. It's not the exact geometry. And also no node is visited twice, again, in a cycle. I have here a node that I cannot travel number 8. That's not a cycle.
If this was an exact geometry, then we can't use it, right?
Fine. If this would be, yeah, but you're not talking about the geometry, you're talking about the connection. So you can still connect this point to go around.
I was thinking in terms of roads over there, I can't like change the road.
Yeah. So if this would be showing specific road connections, then they would clearly cross. But if it's talking about the relationships in a network, imagine these are your computer cables, and there would be a table, so you can take your computer cables around. So the network will still be connected. Yeah, you don't need to cross them, one cable over each other. So the network can still be connected, but you have to go around. Yeah. Then we have exactly two special types of cycles. One is Hamiltonian cycle, and they do have different parameters. So something what you said actually might be the case for some special cycles. So Hamiltonian cycle is a cycle that contains all vertices there are in the graph. So if I walk around in some way that I connect all of the vertices there are, then it's called Hamiltonian cycle. It can repeat the edges, means the lines. I can go through the same lines twice.
So it can be repeat the vertices too?
Yes, and I can visit no, I can't visit the node, but I can travel through the same edge multiple times. So I can visit the vertex, the node, the point only once, but I can repeat the lines.
You repeat the lines, you repeat the vertices.
Not always. I'll draw you an example, because we're talking about networks. So these are my points. I can have them like this. So, pardon? Yes, you can. Yeah, you can think of it as a portion. So you can visit the same path again.
So you can repeat portion of the edges, but not
Ooh.
the vertices. Yeah? Okay.
So vertex only once, but you can repeat the edges. So in this example, with the K4, so this is also a cycle because I can travel. I've visited all nodes or vertices there are in this graph and ended up where I've started. I see you're making notes. So then I never know if I should go faster or not. But next example is Eulerian cycle. And that's the case where it will contain all edges there are. So I can repeat the vertices. I can visit the same points twice or more times, but I'm allowed to visit only the edge on every edge only once. Okay, well, this is an example, but generally, if I think about it, I'm sure you're all familiar. If you have, you know, when you were younger, we have this house. Oh, I missed it. Have you ever done this as a kid? So there's a way how to draw that. No, I keep missing it. I don't know. I need to start some. Damn, I know. So if I go around that, I visit every edge once. I need to practice. I can repeat the nodes, I can repeat the vertices, but not the edges. So that's Eulerian cycle. Whoa. Pardon? I think so, yeah. So, and do the Z. Yeah, yeah. Okay, let's do the correct part. So that's what we call the Eulerian cycle. So that's Eulerian cycle. I have a different example here in this image. So imagine I start in the top right corner, go around, visit the middle, go around, visit the middle one again, do the round cycle, and end up where I've started as well. So, just to repeat, the edges are forbidden. You can only do them once, but you can visit the nodes as many times as you can. And if you remember this game, that's the Eulerian cycle. There's some review or example, which you can practice later. We might put it in the quiz. But a little bit of a history about how Leonhard Euler got his cycle. So it's something he had something that's called a Leonhard Euler's problem. He liked to walk through his hometown, Königsberg, and he wanted to cross all 7 bridges there are, and including visiting the island, and then come back to his home. So imagine that each of these bridges is a connecting edge. So these intersections would be the vertices, the nodes. And he was trying to find if there's a way how he can walk around his city, connecting, that he can cross all of these bridges and come back home. So he was trying to find a solution. So while he was walking, he invented something he invented graph theory. So he simplified the street network into this graph, showing the important crossings. So you can see crossing 1 and 2, these two edges, one bridge, this and this. So he simplified that quite significantly when trying to find some cycle where he traveled. So he could visit the vertices multiple times, but the edge only once. However, the solution, he invented that what we call the Eulerian cycle. He discovered that it's not true for his own hometown, because to be able to cross every bridge only once, the degree of all of the nodes, of all of the vertices in his graph have to be the same. Either all will be 3, or will be 4, or will be 5. If this would be the case within his graph, it means that he can travel through his even node, not the same but even, either 2, 4, 6. However, if you look at this, it's got 3, 3, 3, and 5. So based on his theory, he could not do that. Based on these paths or Eulerian cycles or Hamiltonian cycles, it comes into play where we talked about typical network problems, like this one salesperson problem, that he wants to visit all of his customers, all of his clients in different cities, do a round trip and then come back, and he's trying to do the optimal path, how to visit all of them. So he doesn't want to visit twice the same customer, but he can use the same path. So this problem is using the principles of a Hamiltonian cycle with the least cost values in the networks. And both Eulerian and Hamiltonian cycles are important in transport analysis. And that brings us to another review of with a review question. So, which of the following terms we use in graph concepts? So we have step, walk, hike, march, path, and circuit. Step, walk, hike, path. Yeah. Seems like you're getting it really good. Step is made up, same with hike, march. Circuit is also made up. If it was cycle, then that's true, but it's close. So I can be forgiving for circuit. But yeah, you were paying attention, that's good. Thank you. And in the last, don't have much time, we will talk about network representations. How do we actually represent the networks? The algorithms at the core of the GIS, of the network data.
At the end, all these operations that we saw are also graph operations, because the title is network operation. There's no distinction between network and graph.
Network is a weighted graph, so it's still the same. Yeah. You can do the same analysis both in networks and in graphs. So, however, how does GIS, the geographical software and systems, internally represent the networks? So how do they translate these principles into their understanding and coding? I'm not talking about database structures. It's more about how to represent these relationships between nodes and edges and connections. So we have something which is called adjacency matrix. So we have all of the nodes, all of the edges, they're on the sides of this matrix. So we have them both as a column and as a row. And then thinking if there is a relationship, we use 1 for true. If there is not a relationship, we use 0 as false. So this is how the relationships between nodes are represented. For the undirected, it's an example of the top one. For the undirected, it's a symmetrical matrix where you can see that the top right triangle is identical as the bottom left triangle. However, in the directed graph, it's not the same. We can't say that it's the symmetric matrix. Because there are different relationships in directed graphs. How do we measure the degrees of undirected path and the indirect, or of both in directed or undirected charts? If using this brushing, so we can count, we can just sum the number of ones, both in each row, column or a row, and it will give us the number of degrees. So point A has 1 degree in that direction, in our direction, which is only to point C. And in direction, it's from B and D, so it's 2. So summing the ones in horizontally will give us the, or depends how you set it up, will give us the out degree, and vertically give us the in degree. For the undirected graph, is the same, and it will give us the number as well. So we set up an adjacency matrix. So we can look at this. So we can set up a matrix where every edge describes the connection. So this is an undirected graph. So it is, the triangles are identical. It's symmetric. We don't consider cost in the adjacency matrix. Just saying if there is or is not a connection. However, we can set up a cost matrix, and we use the parameters we know from the adjacency matrix to define that. So if we know that there is no connection, if the value is false, if it's 0, if we know that there is no connection, then we have 2 options. If it has no connection, but it's along the diagonal, if it's going through the diagonal, means that I'm going from point A to A, means I'm already there, so it doesn't cost me anything. So that's the first option. If it's a 0, it's either the same one, this is this case, so it costs me nothing. The second option is, in a case there's a 0, is that there is no connection between point, for example, between A and F. So no matter how much I pay, no cost will actually get me from point A to F because there is no connection defined. So we'll set it to infinity.
You spoke about one of the conditions where you can have wait at nodes also, right? Time for
Yeah.
So in those cases, how do you handle it? Do we have the same kind of?
That would be the same. This is a cost using the money. And these are the conditions. First, I do the adjacency matrix to see if there is a relationship, if there is a connection between 2 nodes. Yeah?
But if I have the point 0 for A to A,
Oh, okay. If you yes, then that's the case. But if you're already not still, it wouldn't be for the diagonal. If you're already there, if you're going from point A to A and you're already there.
Waiting over there, and that's my cost. So how will I add that?
That's a different thing. You're already there, so you don't need to wait there. So it's your choice that you're waiting there. The waiting at the spot which is both your starting and destination, that's not a good example. However, if it would be, and I'm talking about the edges here, not about the points. So you would create a different matrix which would then include the nodes as well. This is just for the lines. Don't think about anything that's there. That's not included in this matrix. No, this is just looking at the connection. It's a good question. I like your thinking, but this is.
In the map, like if
yeah.
You said that it's my choice to wait over there, but there are times when one of my buses is coming and the next tram will be coming after some time. I have to wait over there for some time.
Yeah, yeah.
In that case,
I guess it'll make sense with the next. We won't have time to go through it today. When we actually will trying to find the shortest path, I'll show you some algorithms, but we'll do that next week. Seems that my time is limited. Let's just finish this. So if the value is 0 in the adjacency matrix, I have two options. It either stays 0 if it's on the diagonal, or if it will be set to infinity, it means there is no connection. So no matter how much I pay, I won't reach the point. I'm not able to go from point A to C because there is no connection. However, if there is a value 1, then it will have exactly the same value there is. So I know, so I can set it up so it's $2, those two, 1, 2, 5. Yeah? So if there is a connection, if there's 1, it's true, then I give it the value. And knowing this, we can then go into database models and some logically implemented structures, SQL, and how all these things work in network, but you will learn more about that in subject spatial databases. So that won't be covered just now, but next week we'll start with network search. And that's it for today. Thank you.
On the slide. So the cost matrix, what if